It's a composite positional tolerance using rectangular coordinate dimensioning. All right, that's the first thing. The upper part of the feature control frame specifies a pattern locating control. Oh, okay, of 10 thousandths at MMC. And the pattern of features must lie in a group or as a group relative to datum A and D at maximum material boundary. Okay, so even though the circle M is not next to A, but I mean they're relative to datum A, comma, and datum D at MMB, circle M, and datum B. So it's related to A, D, and B, and D is at maximum material boundary. So D, remember, is a diameter. So at maximum material boundary of where that boundary of the axis would end up, okay, at maximum material condition, which is when the hole is at its, the position tolerance is at its smallest, right? We depart from MMC toward LMC. So when that hole, that large hole is datum, the axis of it is datum D. So when it is, 14 thousandths of an inch over to the right, let's say it's been produced and it's over to the right, then this pattern as a group of holes can be over 14 thousandths as a group. All right, then the next thing, the lower feature control frame, is a feature relating tolerance at 2 thousandths relative to datum A. Okay, so perpendicular to A, right? Let's see, where's A? Oh, A is the back of the part. So it's held in position, each hole must be in position within the pattern at 2 thousandths of an inch diameter tolerance zone at max material condition. Very tight control, a whole lot tighter than this. So the hole is allowed to fluctuate quite a bit, 14 thousandths off of the axis. And the pattern of holes is allowed to be within 10 thousandths of that, but each hole has to be within 2 thousandths of that. Okay? So our challenge is to kind of get a visual picture of that in our mind. Sometimes that's not possible. Sometimes you've got to actually sketch out worst condition for all three situations so you can kind of get a visual of where it would be. You know, you could use AutoCAD to do that. You know, draw a circle, show a center, draw a circle on top of that representing one zone, draw your patterns, okay, and where they could be representing that 10,000 zone. See what I'm saying? Just kind of like what they've tried to show in the book. You know, to try and get a visual. It's so virtual, you know. It's not tangible. You can't, and we're dealing with axes here, which you can't touch on a part. Okay? We find an axis by figuring out where the hole is, measuring where the hole is. Okay? All right? So, composite positional tolerance has to be mentioned. Your upper part is at 10 thousandths MMC. Describe that. The lower feature control frame specifies feature relating positional tolerance at 2 thousandths relative to A, and the feature relating zone is free to shift. The feature relating zone, okay, 2 thousandths, is allowed to shift within the boundaries of the pattern locating zone. Feature axis must be within the boundaries of both zones. Okay, the axis. All right, next, 437. Okay, so we got 3 holes. And And this one is a it's kind of a funny word, two single segment feature control frame. All right, this one, the upper part of the feature control frame specifies your pattern of 14 thousandths MMC, where the pattern features lie in a group relative A, B, and C. No modifier. Okay, so that means regardless of feature size. So no matter what size is manufactured, A, B, and C, this tolerance applies. So it doesn't care. All right, you want to put it in human terms. All right, the lower feature control frame specifies datums A and B. That datums A and B control the orientation of the alignment of the 2000s position tolerance zone at MMC. Okay, where the individual features must lie. Individual features within the pattern must lie, to be grammatically correct, or must lie within the pattern. Both the pattern locating zones and the feature relating zones must remain the same distance from the secondary datum. Okay, since B is the one common. Okay, A, of course, is perpendicular. Then B, which is from this edge, all right, and basic dimension of 4.05. All right, 437. Mind benders. Some of this position tolerance stuff can be. All right. Why is there a separate feature control frame for the hole and counterbore? So we're looking at the counterbore, the .188 counterbore up here. Okay. So there's a separate position tolerance for the hole and the counterbore. The position requirements are tighter for the hole. Okay, so the hole listed first right here, and it's 7 thousandths. Doesn't really fully answer why there's a separate feature control frame, but except that we want to control the hole differently than we do the counterbore. Now, when you're talking about using a counterbore, what kind of fastener is going down in there? Why do we use a counterbore? What kind of fastener fits inside of a counterbore? Any idea? Okay, it wouldn't be a flathead screw. We'll X that one off. Okay, wouldn't be flathead, you know, which is countersink. All right, so what kind of fastener goes down in there? You may have seen them on various assembly, if you're putting things together, or any kind of metal furniture. A lot of times you might have it in your, okay, a socket head hex, okay, socket head hex screw, okay, that you use an Allen wrench on, or a hex wrench on. All right, so a socket head, usually in industry, in manufacturing or machining, machine assembly and whatever, that's common as dirt. If you got a counterbore, there's going to be a socket head hex screw going down in there that you use an Allen wrench on. Now, occasionally we might have a socket or a counterbore and put a standard old hex head down in there. But if you do that, the counterbore has to be very large, because you got to allow room for the socket to fit in there. and have room to play. You know, if it's very deep, then it's got to be pretty large so that you can wiggle and get it in position and get it off. All right, in case it gets stuck. All right, so those kind of things have to be accounted for. But there is a standard socket head measurement for a type of socket size screw, socket head screw. All right, so what is doing the positioning on a counterbore shape? What is actually holding the part in position? Which part of that? The top dimension or the second dimension? The hole or the counterbore? What actually holds the part in position? Which one of those features? The hole. It's called the pilot hole, or the hole. Okay, and that's going to touch the sides of the screw. Some screws have a long shank on them, no threads, that is of a higher precision and controlled diameter, and that may be important for assembly of this part and actually touches the sides of the screw shank, okay, and holds it in position. So apparently, I mean, that's pretty tight control for a screw hole position. Okay, a pilot hole, 7/1000 in position, 7/1000. 2.5 hairs, roughly. It's pretty tight control. Now, you look at the counterbore, well, they made it 14/1000. Well, listen, when you make a counterbore hole in the machine shop, they're going to use a tool that's got a pilot shank on it, just a smooth bearing surface, and they've already drilled the hole. Then they'll bring the counterbore tool in and cut the counterbore. So they doubled it. They knew what position they needed for controlling the position of the part, and they just doubled the counterbore, you know, just for good measure. That's still pretty tight. 14/1000, that's less, that's 1/1000th of an inch less than a 1/64th of an inch. And counterbores are kind of run on 64ths. Okay? All right? So the critical thing here is the position of the hole. All right, so why is there one for the hole and a counterbore? So that we have a separate tolerance for the hole, and we're trying to locate the hole in a greater precision. B, we have hole and counterbore, and we're doing our little math. They're both holes, and they're specified at MMC, so we do have bonus tolerance allowed. So starting at the smallest for the hole, 0.187, your position tolerance would be what? It's right next to the circle M. Your positional tolerance for the smallest hole of 0.187 will be, since it's circle M, okay, there's no math required. Exactly. Okay, there's no math required there. It's not a trick question or anything. No math. Okay. Positional tolerance at MMC, okay, 7/1000 circle M. So as soon as you see the circle M, you know what your position tolerance is going to be at max material condition. It's next to it, okay? That calculates it automatic. Then as we produce different sizes up to LMC, we're allowed to increase. So in your little chart there, it's going, first of all, jumps 1/1000, then it jumps 2, then it jumps 1. So you just add it to it, okay? So your next size would be 8/1000. Then for 0.190 it'd be 10 thousandths. Then for 0.191 it'd be 11 thousandths. All right, so with that in mind,